In today's video, we're going to be looking at multiplying decimals. And so to start out, we'll be looking at a whole number times a decimal using three different strategies. First, how we can leverage place value and place value language using equivalent fractions, and then finally getting into the algorithm. Once we've reviewed those strategies, then we'll move into decimal times a decimal, and that one will just focus on the algorithm because that is going to be the most efficient and most common strategy. So if we start out and we have an example like 4 times 3/10, just to refresh on what multiplying is, this is the same as saying that you have 3/10 4 times, or 4 groups of 3/10. And going way back in the day as a mathematician, you know that you could also think of this using as repeated, that's not how you spell repeated, repeated addition. And that means that we could be adding 3/10 plus 3/10 plus 3/10 plus 3/10 4 different times to show our 4 groups of 3/10. So to get us started, I'm just going to quick solve that addition so that way we have a ballpark on where we're going, and thinking about what would be reasonable is always going to be a helpful strategy here. So actually, I'm going to do a quick blue box. So I know in here, this is going to be where I'm going to write my reasonable answer. I know that 3/10 is close to 25/100, and I'm picking 25/100 because I know that 4 times 25/100 is equal to 1 whole. And so that's some math that I can do pretty easily in my head, and one of the numbers is changed but related still. Now, because I took 3/10 and I'm multiplying by a number that's less than that, my answer here in my reasonability is going to be less than the actual answer. So I know that I should be expecting a number that is greater than 1 when I do my actual calculations. So I have my reasonability. I know I'm going to be somewhere near 1, but greater. I'm going to add these up just to see. I know 3/10 plus 3/10 is 6/10, and then 6/10 plus 6/10 is 12/10, or 1 2/10. So this does fit with our reasonability. We know this is close to 1, but a little bit greater. So let's look at how we can use place value language to solve this one. So we are solving 4 times 3/100, and this is where it's why I've been such a huge stickler on when you read this, read that as 3/10. I think I said hundreds a moment ago. Because if we think of that as 3/10 instead of 0.3, we know that we actually have 3/10, if my Apple Pencil would work today, times 4. And so if I use this tenths as almost like a unit, I'm basically just doing 3 times 4, and I know that's 12, and my unit here was tenths. Because those 3's are tenths, they're not just 1's. So 3/10 times 4 is 12/10. And I have a couple different ways of thinking about turning this back into a decimal. This is either a 12 that ends in the tenths place. So that means I'm going to have to put my decimal point right there. Or I know as a fraction, this is 12/10, which is 1 2/10, and that converts to that decimal there. So that's our place value language. And that is a great strategy when you have a whole times a decimal. It gets a bit tricky when you have a decimal times a decimal, but it's nice, a good like mental calculation strategy for multiplying decimals. Next, we're going to move into how we can use fractions to multiply. And so if we have 4 times 3/10, I'm going to convert my decimal because that's the piece that gets tricky in here. The whole number is less of an issue. So I'm going to convert that decimal into a fraction, and I know 3/10 as a decimal is the same as 3/10 as a fraction. So 4 times 3/10, if you need to think of it as 4 over 1, multiply straight across, you get 12/10, or 1 2/10, which is again equal to 1 2/10 as a decimal. So this strategy would also work if, let's say that this was 4/10 times 3/10, and we'll look at this in the next little bit, but it would work out the same way, where you just convert them both to fractions, and then you would multiply straight across. Now keep in mind, this is tenths times tenths, so your answer is 1/100, And 12 hundredths is a 12 that ends in the hundredths place. So that's for a little bit later, but just a quick preview that. So now we're going to be looking at the algorithm for 4 times 3 hundredths. And when you set up the algorithm, you want to put the number that has the most digits on top, not the value, but the most number of digits. And so let's set this up, and then we'll put the 4 underneath here. You kind of have to ignore the decimal. And now you're just going to count the places to the right of the decimal. So here, I'm going to put this as a 1 in a circle because I know there's only one digit that is to the right of the decimal. So if I do 4 times 3, so now you just multiply like they're whole numbers. And 4 times 3 is 12. And because we had one place to the right, that means I need to move my decimal point over 1. And our answer is 1 2/10, which fits. So a quick background on why. When you do this multiplication as just 3 times 4, I know that 3/10 times 10 equals 3. So when we get this 12 here, this is actually 10 times 2 great. And so to undo that, we would need to divide. You would need to divide by 10, which would then shift that decimal point back over. So again, the algorithm, you just line them up with the most digits on top, ignoring that decimal point, count the places to the right, and give yourself that reminder there that it is going to be 1. Then you do your multiplication, and then put your decimal point back in that number of places. So let's jump into decimal multiplication. So let's say we have 13 hundredths times, I already used lots of 4s, so let's just say 5 tenths. So we're really just going to focus primarily on the algorithm, and a reasonable answer on this one, over here, reasonable answer. We know we have 13 hundredths times 5 tenths. 5 tenths is equivalent to half, and so I'm going to think of this as what's half of 12 hundredths divided by 2. And that's going to be somewhere near 6 hundredths. So I know my answer is going to be somewhere close to that. So keeping that in mind, I am going to set this up following the algorithm, where we know there's more digits in 13 hundredths. I'm going to kind of ignore those decimal points for now, which is different than subtraction and addition. And now I'm going to quick count. I know there's 1, 2, 3 digits to the right of the decimal point. So I'm going to leave myself that reminder. And now I'm going to multiply. 5 times 3 is 15. Record the 5. Regroup that 1. 5 times 1 is 5, plus 1 is 6. And all the rest are going to be zeros. So because I have 3 places, my decimal point right here, we need to move it 1, 2, 3. So that's where our decimal point is. And in order to keep those digits in the correct place, I need to fill in that 0. So we calculated and got 65 thousandths. And if we look at our reasonability answer, that is pretty close. So let's just double check ourselves. If we solve this like fractions, I know 13 hundredths looks like that as a fraction, and then 5 tenths looks like that. So I'm just going to multiply straight across, and I know 13 times 5 is 10 times 5, 50, 3 times 5, 15. So that's 65 thousandths, or a 65, where this is the thousandths place, hundredths, tenths. There's our answer. Boom.